Up to here, you should have been able to find the dual of a normal maximization and normal minimization linear programming. Now let's see how we can find the dual if the given primal is a non-normal linear programming. Just a quick reminder, in normal max problem, all constraints must be greater than or equal to, and then all variables must have the sign restrictions of greater than or equal to 0. In a normal minimization problem, all constraints must have the sign of greater than or equal to, and all variables must have the sign restrictions of greater than or equal to 0. Now let's see a problem that is non-normal. So the one that is currently shown on your screen is a normal maximization. Let's compare that with this. So in this example, you notice that it is a maximization problem. However, you see that the first constraint has the sign of equality, and the second constraint has the sign of greater than or equal to, and then you also see that the second variable x2 is a URS variable. So clearly this is a non-normal maximization problem. Just like before, we're going to use this table to put the information about the primal and then use it to find the dual. Because the primal is a maximization, I'm going to first cover the minimization part because it is related to the dual. Okay, so this is our given primal problem. It is a maximization, and then we have two variables, x1, x2, and then we write down the constraints for each row. So put the constraints like this, and then for the objective function coefficient, we put it on the bottom of the table. This is 2 and 1, so 2x1 plus 1x2, and then we put the sign restrictions there above the name of the variables. So this is our primal LP. Now let's fill the table with the information that we need to find the dual. First, because the given primal is a maximization case, our dual is minimization case. So we write down minimize W. We have three constraints in the primal, so we have three variables in the dual. So we write the variables y1, y2, y3 because our dual is a minimization case. Now for the sign restrictions for each variable, here's where you need to be careful. The first dual variable comes from the first primal constraint. In the primal constraint, you see that the sign is equality. Whenever the sign of a constraint is equality, the corresponding dual variable is URS. So that's why here you write down y1 URS. The second dual variable comes from the second constraint. And then you see the second constraint has the sign of greater than or equal to. And your primal problem is maximization. In the case of maximization, the sign of a constraint that is greater than or equal to is not normal. Because the constraint is not normal, the corresponding dual variable is also not normal. A variable is not normal if it has the sign restriction of less than or equals to 0. Okay, let me repeat. The second constraint in the primal is not normal. It's not normal because the sign is greater than or equal to. As the result, the corresponding dual variable y2 is also a non-normal variable. A non-normal variable looks like this. The sign restriction is less than or equals to 0. Okay, for the third constraint, this constraint is a normal constraint in a maximization case. So as the result, the dual variable y3 also is it is also a normal variable, and a normal variable in the minimization case has the sign restriction of greater than or equal to 0. So the sign restrictions of the dual variable, they are related to sign of the constraints in the primal variable, which means that the sign of the constraints in dual variable is related to the sign restrictions in the primal variable. Okay, so those signs comes from the fact that x1 is a normal variable. It is normal because the sign is greater than or equals to 0. As the result, the constraint sign in the dual is also normal. For minimization case, which is our dual, the sign of a normal constraint is greater than or equal to. x2 in the primal is a URS variable. As the result, the second constraint in our dual variable has the sign of equality. So remember, if a variable has the sign restriction of URS in primal, it will become an equality constraint in the dual. In other way, if in the primal it is an equality constraint, it will become a URS variable in the dual. So equality constraint always corresponds to URS variable, both in primal and dual, and vice versa. Okay, so again, the reasoning is because the second constraint in our dual comes from a non-normal x2 variable. And the non-normality here is because the variable is a URS. So the table is complete. Our dual is minimization. So for this table, we always read the minimization by reading the table down. Okay, so let's start with the constraint. This is how you read it. 1y1 plus 2y2 plus 1y3 greater than or equals to 2. That's the first constraint. Second constraint, do the same thing. y1 minus y2 plus y3 equals 1. So that's the second constraint. Sign restrictions are straightforward. And then for the objective function, minimize w equals 2y1 plus 3y2 plus 1y3. Okay, again, you just ignore these signs because they are the sign for the constraints in the primal problem. So we have obtained the dual. So to summarize and to highlight the non-normality, let me show you that this is our given primal, which is a non-normal maximization. And then this is the result that we have obtained in the previous slide, which is a non-normal minimization for the dual. So let me highlight that the second variable is URS. So the second constraint is equality in our dual. The first constraint in primal is equality. So the first variable in our dual is URS. The second constraint is non-normal in our primal. So our second variable in the dual is also non-normal. Now let's find the dual for non-normal minimization. Here you are given the normal minimization. Compare that with this. You can see that the third constraint is not normal because the sign is equality. The fourth constraint is also not normal because the sign is less than or equal to. And then for the variables, the first variable is not normal because it is URS. Okay, while in the normal minimization, the variable sign restriction must be greater than or equal to 0. So clearly this problem is a non-normal minimization. We are using this table again, and then I will cover the maximization part because it is related to the dual. Okay, so because this is minimization case, our primal problem is minimization case, we will fill this table by columns. Okay, so the first constraint, 1y1 plus 2y2 plus 1 times y3, you write it down like this: 1 times y1, 2 times y2, 1 times y3 greater than or equals to 0. So the second column is 1, 0, minus 1 because 1, 0, y2 minus 1, y3 greater than or equals to 1. You have 4 constraints, so you have 4 columns here. Okay, and then sign restrictions, they're straightforward. You just write them down there. And then here for the objective function, 2, 4, and 6, you put it here, 2, 4, and 6. So those are all the information from the primal LP. Now let's find the dual. Because the primal is minimization, the dual is maximization. And then because we have 4 constraints in the primal problem, so the dual will have 4 variables, x1, x2, x3, and x4. Now for the sign restrictions, let's see. In the primal, the first constraint is normal. So the first variable in dual is also normal. A normal variable in maximization case is greater than or equals to 0. The second constraint in dual is also normal. So the second variable also has the normal sign restrictions greater than or equal to 0. The third constraint in our primal has the sign of equality. So the variable in our dual has the sign of URS. Finally, the last constraint in our primal is less than or equal to. This is not normal. So in the minimization case, this is not normal. As the result, the fourth variable in our dual is also not normal. So x4 less than or equals to 0. This sign restriction is not normal, okay, because it comes from a constraint that is not normal. And then for the signs of each constraint, it comes from the sign restrictions. So the first constraint in dual, because our dual maximization, so we read it by row. The first constraint in our dual comes from the first variable in our primal. The first variable in primal is URS, so the sign of our constraint, so the sign of our first constraint in the dual is equality. The second constraint in our dual comes from the second variable in our primal. The second variable in primal is a normal variable, so the sign of our second constraint is also normal. For maximization, the normal sign is less than or equal to. For the third constraint, it comes from the third variable in the primal. In the primal, the third variable is a normal variable, so the constraint is also a normal constraint, which in maximization has the sign of less than or equal to. Okay, so now we're ready to read the table to obtain the dual. Because our dual is maximization, so we are going to read the table across the row like that. So that's the first constraint. This is the second constraint. This is the third constraint. Sign restrictions are here. And for the objective function, you read it 2 times x1, 1 times x2, 1 times x3, 3 times x4, and you just ignore the signs in front of these numbers because they belong to the sign of the constraints in the dual. Okay, so up to here you should have been able to obtain the dual of a given primal LP, whether the given primal LP is normal or non-normal, whether the given primal LP is maximization or minimization. You should be able to find the dual. Okay, in the next video, I'm going to ask you some questions to check your understanding. So see you on the next one. Thank you.